I would like for all of us to imagine we have spent years saving up for our dream trip to Europe, specifically to Paris, France. It is the morning of July 17th, 1996, and we are finally boarding the flight to go on our trip to Paris. Unfortunately, for us and 230 other passengers, this flight will never make it past Long Island, New York, and will go on to affect hundreds of lives and spark one of the biggest aviation investigations in the United States. Hello, I am Avery Skinner, a student at UW-Madison, currently studying civil engineering, and our presentation today is going to focus on the tragedy of TWA Flight 800. In the history of aviation, certain events and flight outcomes have raised many questions regarding safety standards, responsibility, and ethics within the aviation industry. One of these events includes TWA Flight 800. Flight 800 has many mysteries and conspiracies surrounding it, with many today still believing that the flight was blown up by missiles. In today's presentation, we're going to dive into the research and highlight ethical dilemmas and the delicate line between profit and safety for many corporations, as well as the changes it made to the flight industry. To start off with research, I'm going to pass the presentation off to Livy.
I'm Libby, I'm a team researcher, and I'm here to tell you about Flight 800. On July 17, 1996, Trans World Airlines Flight 800 was scheduled to fly from New York to Paris. The Boeing 747 airliner left JFK Airport at around 8 p.m. The plane carried 230 people total, 212 passengers, and 18 crew members. But sadly, no one ever made it to their destination. 12 minutes after the plane took off, it had traveled 8 miles and ascended to 13,700 feet. Starting to cross the Atlantic, the plane still flew close to Long Island's shoreline. This close proximity created an abundance of witnesses as the plane fell into the Atlantic. The center section, shown in red, fell first. The yellow section, the forward fuselage, soon followed. Finally, the rest of the plane, shown in green, struck the water. Newspapers across the country reported on the incident, especially the witness reports stating how a streak of light hit the plane just before it fell. A 10-month diving operation recovered 95% of the plane remnants. In order to decipher what had happened, the plane was reconstructed to the best of its ability. The National Transportation and Safety Board, or NTSB, launched its investigation as soon as the pieces of the plane were accessible. The NTSB initially reported 3 possible causes of failure. The first was structural failure and decompression. This was quickly ruled out due to there being no corrosion, metal fatigue, or structural faults. The second possible cause was the detonation of a bomb or missile. However, there was no evidence to support this theory either. There were no holes indicating the penetration of a missile, and no localized area had any more severe damage than another. While there was trace residue found in the plane, this could quickly be explained by past uses of the airplane. And the light trail witnesses saw could have been burning fuel falling from the plane. The last theory was fuel-air vapor mixture combusting in the wing. The wreckage displayed that pieces of the center wing tank were ejected first. Overpressure in the tank was the first in the sequence of failure. This overpressure was deduced to be caused by the fuel-air vapor mixture combusting in the wing tank. The Aircraft Engineering and Aerospace Technology Journal reported a high concentration of the flammable fuel-air vapor mixture in the wing tank. This, combined with the aging electrical wiring, were the catalysts. There was an electrical short in the wiring that ignited the fuel-air vapor mixture, causing the explosion that brought down the plane. TSB explains how there were no maintenance practices protecting the integrity of the wiring. The Federal Aviation Administration explained how there was a supposedly explosion-proof tank design. This tank design accounted for fuel temperatures and limiting ignition sources. Part of this, explained by a journal of failure analysis and prevention, included keeping a low electrical current in the wiring close to the tank. This system did not take potential wire shorts or vapor buildup into account for its explosion-proof tank design.
Thank you, Livy, for that great summary. My name is Owen Kinnick, and I will now be discussing who and what was affected by the flight, design decisions that led to the crash, and ethical questions posed by the disaster. For all 230 people aboard the flight, it affected them in the worst way possible. They are no longer with us. And for all their friends and family, the flight and its crash still affects them to this day. There were no planes grounded following the crash, as happened with the Boeing 737 MAX jet recently. It took the FAA 10 years to mandate any design decisions or specifications for airplanes that would help prevent situations like this from happening in the future. In 2000, nearly 4 years after the crash, the NTSB released a 350-page report detailing the crash, analyzing evidence, and discussing possible causes of the crash. As Livy mentioned earlier, they were able to rule out a missile strike and structural failure. They determined that the crash was most likely caused by an explosion of the fuel tank due to increased fuel vapor pressure and a spark caused from faulty wiring components. They also determined that everything was up to code and everything was properly maintained on the flight, so there was no human user error that caused the crash. So is this all bad luck and coincidence? Why did this plane crash? Why are these issues taken into account? We can begin by discussing the airplane fuel tank design. The engineers who designed the fuel tank claimed that it was an explosion-proof design, but they only assumed that because they thought that they could assume that there were no possible ignition sources. The tank was, in theory, still flammable. They didn't design it to not be able to explode. They just assumed that there would never be an ignition. There would never be a spark in the fuel tank. This is an incredibly flawed assumption to make. It's impossible to rule out all possible ignition sources. Something could happen, as it did in this case, that caused catastrophic failure. It seems like the type of assumption we'd make in an intro-level engineering class when trying to solve a complex problem, but we're not then getting a super precise answer. You can't make assumptions like that when you're designing a system that cannot fail, that absolutely cannot fail. If it fails, it leads to the death of hundreds of people. The engineers made a mistake in designing the system this way. Continuing to discuss the fuel tank design, another flaw was that the engineers designed no way to reduce the flammability of the air tank. This was an easy problem to avoid because the military had developed a solution decades before. Military airplanes really do not want to explode. They're constantly being shot at, and if a bullet passes through the fuel tank, there's a very high likelihood it could explode if it's because of all the flammable vapor that's in the fuel tank. So the military designed a way to reduce the flammability. They would inject inert gas, usually nitrogen, into the fuel tank, which lowered the oxygen content from around 21% all the way down to 9%. This meant that the vapor in the fuel tank was much less flammable and the airplane was much less prone to exploding. But commercial airline designers thought that this wasn't really an issue because, commercial airplanes usually aren't getting shot at by other airplanes or other things like that. So they overlooked this step and decided that adding this part to the fuel tank was not necessary. But it turned out that if this had been the case, it may have prevented the crash of Flight 800. And it took the FAA almost 10 years after the crash. In 2008, they mandated a system like this be installed on all new airplanes. But it took 10 years after the crash for something like this to be implemented. Given these two major design flaws, it seems as if proper engineering could have easily prevented the crash of Flight 800 from ever occurring. But there have been no similar disasters since 1996, and there was only one similar incident that happened before. So was it actually worth it? Would it have been worth it to spend millions of dollars designing and implementing solutions to this problem when it could have saved the lives of only one plane? Obviously, it seems worth it to those who are on board the flight who are no longer with us and their friends and family. But maybe it was worth it to the executives and people making decisions at airplane manufacturers and airlines.
My name is Chase Peterson, and I will be talking about the consequences of this disaster and the risks involved in not following improvements made as a result. After the largest investigation in the history of the NTSB, some recommendations were given to prevent anything like this from happening again. They include look into manufacturing practices of fuel tanks and how components inside are kept from being ignition sources, review design specifications for wiring systems that are critical to safety and that there's adequate separation from those systems, develop practices to minimize silver sulfide deposits that could cause risk for ignition, improve training of maintenance crews to recognize potentially hazardous wiring systems or wear, better documentation and reporting of wiring conditions, and incorporate technology as safety mechanisms for wiring failures. One change seen today includes design practices that don't overlook small details or parts. Before this disaster, Boeing's design allowed parts less than 3 inches long to be electrically unbonded, which could pose a risk of ignition from static electricity. Today, every part should be treated as significant and should be designed with safety in mind. Another change is maintenance practices that are more thorough and well documented, especially when it comes to an aging aircraft like the 747 in the event. Aging aircraft have more to maintain and require trained personnel to recognize fatigue, wear, aging parts, and safety hazards. Additionally, safety measures are to include technology to prevent wire shorts to prevent fuel tank explosions. The Fuel Tank Flammability Reduction Rule, or FTFR rule, was implemented by the FAA in 2008 to mitigate risks associated with detonation of the fuel tanks. It calls for the design of all new planes to have devices to reduce flammability by means of nitrogen gas or oxygen limitation. It also mandates the retrofitting of planes built after 1991 with these safety devices. The testing of nitrogen gas in fuel tanks rather than flammable oxygen is shown in the picture, which is in the cargo hold of an Airbus A320. If airplane designers and manufacturers today try to cut corners, there will be no positive outcomes for them. There are countless safety risks, from design oversights, lack of safety mechanisms, maintenance failures, and aging failure. That lack of safety or trustworthiness in the company will dissuade airlines from buying those planes and passengers from flying on those planes. The monetary loss from both fewer people wanting to use those planes and from possible fines and liability for failing to follow regulations would be immense. From our research, no party was held legally accountable for this disaster, as it seems to be more of a freak accident than a result of overt neglect or carelessness. However, that does not mean there are not lessons to be learned or improvements to be made. Maintenance codes from the FAA that required more thorough inspections, especially of aging aircraft, and better documentation, in addition to precise attention to detail from Boeing, may have prevented this disaster from happening. An important lesson to be learned is that there can never be too many safety precautions taken when designing and maintaining a passenger aircraft. After these improvements and lessons, we can hope that today our planes are going to continue to be safer and more reliable than ever. Thank you.
Thank you, Owen and Chase, for the great insight on the ethical questions posed, as well as the many risks that were involved in the changes that have since been made within the aviation industry. As a group, we would like to thank you all for listening to our presentation and being here today. We hope you learned a lot regarding the ethical questions and the tragedy of TWA Flight 800. We will now be open to answering any questions you may have. Thank you.